Okay, this is fall 2013, Donna Dietz, Math 154, American University, Practice Exam 2, question 13. So, explain why the harmonic series diverges. So, if H is the harmonic series, and it's looking like this, what I'm going to do is I'm going to regroup like we did in class. I have to write etc. So unfortunately, because the paper is narrow, it's kind of hard. You know what I'm going to do? I'm going to just actually write this out on the next line so that it's a little clearer. Okay, plus 1/9 plus all the way up to 1/16. That's the next group. Plus 1/17 all the way up to 1/32. Now I can say etc. and it should be clear. There we go. Each of these groups is equal to or greater than 1/2. You will see 1 is greater than 1/2 over here. 1/2 is 1/2. Then 1/3 plus 1/4 has to be greater than 1/2. So you note, just example, note larger than 4/8, which is 1/2. But each of these groups you can say that about. So 1/9 through 1/16, there's 8 fractions here. And 1/17 through 1/32, there's 16 fractions. Each group, for each group, the number of fractions doubles. Okay, so that's what the harmonic series is. So L is something that is less than the harmonic series, is 1/2 plus 1/2 plus 1/2. So for example, right here, this guy goes down here. Okay, did you see that? And for example, this guy goes here, this guy goes here, this guy goes here. That's ugly, so I'm going to get rid of those. But you see where they're coming from. And L goes to infinity. So since H is greater than or possibly equal to L, because they're both infinity, then H goes to infinity too. Both of them have to go. So if you're smaller, or if you're bigger than something that's infinite, then you're infinite. If you're bigger than infinity, you're infinite too. There we go. Okay, next question. Oops. Explain why the alternating harmonic series converges if the terms are taken in the given order. Aha! So A is the alternating harmonic series. There we go. There we go, etc. See what's happening? Okay, so that is going to be like we talked about in class, 1/2 plus 1/12 plus 1/30. And again, we have to agree to take the terms in exactly the order they're given. That's 7 times 8, not 78. 9 times 10. 11 times 12, and so forth. But does this go infinite just like the other one did? Well, no. Because some geometric series we know looks like this. 1/2 plus 1/4 plus 1/8 plus 1/16 plus on and so forth. This guy is equal to 1. Right? In my answer key, I gave you one that adds up to 2. And that's okay. But this one adds up to 1. And let's see. 1/2 is the same. But you notice 1/4 is much, much bigger than 1/12. 30th is much, much smaller than 1/8. If you compare these term by term, you must be smaller than G. So if CA, so first of all, G is greater than 1/2, because just look at it. Look over here. There's terms, right? I'm sorry, that's not what I meant to say. I meant to say A is greater than a half. I mean, G is also greater than half, but A is greater than half. That's the important point. So A is greater than half because at least it's a 12th greater than a half, and then a 30th greater than that. So A is greater than half, and A is less than G, which is equal to 1. So A is somewhere between 0.1 and 1. And that's all we care about. We don't care where it is, but it has to converge to something which is real. It's somewhere on the real line. If you had a real line sitting here, 0, 1, 2, whatever, -1, then, I don't know, maybe it's here, somewhere like that. That's all we're saying. We're not saying anything profound. We're just saying it is something on the real line. It does not go off to infinity because it can't get bigger than 1, can't get less than a half, so it's somewhere in there. That's all we're saying. Okay, and if you want to narrow that down, you can keep adding terms and getting closer and closer and closer and figure out as many digits of that thing as you want. So that means it's converging. Okay, that's all.